We shall have a short review about the optical properties of quarter wavelength thick layers. Here's a model in Matlab live script, and let's take a look at the code. Since we have already made the T-matrix function, the code to calculate layered materials is quite straightforward. In this case, we have two layers whose refractive indices and thicknesses can be modified. The layer number 1, its thickness, layer number 2, and its thickness are presented by the slider controls. The substrate index can be set separately, and we have selected refractive index of 1.53. The wavelength range can be set, the incident angle, and then we use the for loop to calculate the reflectance at each wavelength point. We use the repmat function to repeat this vector n periods. And we use this for the refractive index vector as well as for the thickness vector. And first we set the number of periods to 1. So we have just 2 layers on top of a substrate. The rest of the code is just for plotting the results. Let's first illustrate the anti-reflection property of a single quarter wave thick layer. We select an refractive index which is smaller than the index of the substrate. So let's use 1.45 for the index next to the substrate. And by tuning the thickness, we see that the reflection is indeed reducing. However, to reach the complete anti-reflection, the index we select for the layer has to be square root of the substrate index, 1.24. So let's select, and now we use 600 nanometers as our center wavelength. By using this index, we can calculate the quarter wave thick layer thickness, 120 nanometers, and indeed we see that the minimum is now at 600 nanometers. When we tune the thickness, we see that the minimum is moving and new minima are emerging. When we increase the thickness by a layer which is half wavelength thick, so 360 nanometers, we again have the anti-reflection at 600 nanometers, but its bandwidth is now smaller. And always by adding half wavelength to the thickness of the layer, we reach the same position, however with a narrower bandwidth. Next, we investigate high index quarter wave thick layers. Let's select index that is higher than the substrate, say 2.35, and we see an increased reflectance. To position the reflectance peak to 600 nanometers, we again calculate the quarter wave thickness, 63 nanometers, and the reflection maximum is now positioned at 600 nanometers. Again, when we tune the thickness, we see that the maximum is moving and periodicity of the reflectance is emerging. Let's again increase the thickness by a half wavelength. 191 nanometers, and we'll see that the maximum is at 600, again with the narrower bandwidth. As a third example, we shall use 2 or more quarter wave thick layers. And in this case, we select refractive index of 1.45 for the first layer, and then its quarter wave thickness is 100 nanometers. And below that, we use the high index layer with a thickness of 60 nanometers. And let's increase the number of layers. We see that with increasing number of periods, the reflectance around 600 nanometers is increasing over a certain bandwidth. This structure is called a Bragg reflector or Bragg mirror. By selecting the thickness of the layers, very high reflectance can be realized on any wavelength, provided that we use low loss layers to realize the mirror. We can still plot the refractive index profile by using, for example, the bar function. And here we have the structure of the mirror, which is the repetition of low index and high index layers. And in this case, the number of periods is 10.